today we're going to be talking about polynomials. Okay. So polynomial is any expression of the form an x to the n plus an minus 1 x to the n minus 1 plus an minus 2 x to the n minus 2, etc. So a1 x to the 1 plus a0 x to the 0, which is just 1. And you normally call this p of x. Or you can give it any name you want, but that's kind of convention. Okay, so some terminology about polynomials. The degree of a polynomial, which is denoted by dEgp, is the highest exponent that appears in that expression. So in this case, that would be n. You all agree with that? And these here, a0, a1, a2 to an, are known as the coefficients. Specifically, a0 is called the constant coefficient because it doesn't depend on x, and an is known as the leading coefficient because it's leading in the expression. Okay. A root of p is any value r that satisfies p of r is equal to 0. And p is called monic if an is equal to 1. Okay. Just that term sometimes comes up, so it's useful to know what it means. Okay. So, if you have two polynomials p and q, then p plus q is also a polynomial. P minus q is also a polynomial. P times q is also a polynomial. And p divided by q is not a polynomial. Specifically, something of the form px over qx, where p and q are polynomials, is known as a rational function. So just like a rational number, yes?
So let's say q divides into p, leaving a whole. Is it a polynomial?
Yeah. So all polynomials are rational functions, but not all rational functions are polynomials. Okay. So how we saw yesterday that a rational number is one integer divided by another that's not 0. A rational function is defined in the same way. So you can see it as, for instance, 2 over 1 is a rational function and an integer at the same time. Okay. Okay. First theorem that we will look at. Fundamental theorem of algebra. So by the name you can tell it's quite important. What that says is that for every non-constant polynomial with real So every non-constant polynomial with real coefficients can be written as a product of polynomials with real coefficients and degree at most 2. So does that kind of make sense to everyone, the statement at least? Okay, well, we'll do some examples. Okay, well, so yesterday we did factorization with simple expressions, but this theorem says that in general, if you have some polynomial, it can have 2019 terms in it, so like a billion terms, you can always simplify it into just a product of quadratics and linears. So to write it in a different way, you can write p of x as an times by r1 x r2 x r3 x to the sum rkx, where the degree of ri is less than or equal to 2 for all I. Okay? This is sometimes useful for polynomial questions. We can do an example. Okay, so consider x cubed minus 2x minus 4. Does anyone know what the factorization of that is, just by looking at it? Do you want to try? Okay. So this turns out to be x minus 2 times x squared plus 2x plus 2. Okay? It's not a particularly interesting example. It just shows that you can take a cubic and always factorize it up into linear terms and quadratic terms. Okay? But you can also get all of the terms linear if you have the right polynomial. So something like x cubed minus 2x squared minus 5 x plus 6 would be x minus 1 times x plus 2 times x minus 3. Okay? So it is possible to get everything to be linear. But this isn't restricted to just cubics. You can do higher powers as well. For instance, the one we looked at yesterday was x to the 4 minus 1. So if you now factorize that, hopefully that's x squared plus 1 times x minus 1 times x plus 1. So you can see that that's consistent with the finite theorem of algebra. Okay. But keep in mind that these factors that you get out aren't always nice to work with. For instance, consider x to the 5 minus 1. Now, does anyone remember how that factorizes from yesterday? So it's x minus 1 times x to the 4 plus x cubed plus x squared plus x plus 1. If you look at the formulas that we did yesterday. But at this point, you notice that this is a polynomial of degree 4. But according to the fundamental theorem of algebra, that can also be factorized up into linear terms or quadratic terms. Cool. So don't bother trying to find it, because it turns out it's x minus 1 times x squared plus 1 minus the square root of 5 over 2x plus 1 times x squared plus 1 plus the square root of 5 over 2 plus 1. You can check that if you want to, but yeah, so don't always back on being able to factorize it nicely. Okay? Okay. Next up, we can use the fundamental theorem of algebra to help us find the roots of polynomials. So,
it's basically saying numbers can be written as a product of their quadratic and linear factors.
yeah, exactly. So I don't know if you've done the fundamental theorem of arithmetic yet before. So you can write every number as a product of two prime numbers, of some number of prime numbers uniquely. You can do the same thing with polynomials. Okay, so consider some root of p, which means that p of r is equal to 0. Okay, but we have that p of x is equal to this mess over here. So that means that an times r1 of r times r2 r times up to some k r is equal to 0. Right? Okay, now also I forgot to put that in the definition. So the leading coefficient is always non-negative. Okay, so in this case, you have some product of things that gives you 0, and this term is not 0, which means the product of this stuff has to be 0. Okay, yeah, so if you have a product of things and they're equal to 0, you know that one of them has to be 0, which means that so there exists an I less than or equal to k, such that Ri of that root is 0. So this is significant because it means if you want to find the roots of a polynomial, all you have to do is factorize it into linear and quadratic terms, and you can find the roots of those. You can find the roots of the original polynomial. Okay. So we need the way of solving linear and quadratic polynomials, so then we can solve everything. So a linear polynomial is one with the form ax plus b. If you let that equal to 0, you get that ax is b minus b, so x is equal to minus b over a. Cool, so you can do that. Yes, yeah, I'm sure you all know how to do that part. Next up, consider a quadratic. Ax squared plus bx plus c should be equal to 0. Yes? Okay, and we can solve this by using completing of the square. We first get rid of the leading coefficient, so it's easier to work with monic polynomials. So divide through by a to get x squared plus b over ax plus c over a is equal to 0. Now, you do a little trick where you see that this is x squared plus b over ax plus b squared over 4a squared minus b squared over 4a squared plus c over a is equal to 0. Do you all agree that these two things are equivalent? Yes?
Where did you get the 4?
Magic. No. So you'll see now why. Well, I mean, I could have put this to be like a 6 and a 6 over here. And it would still be true, but it won't be useful in this case. In the next step, you'll see why. Okay. So you notice that this is x squared plus 2 times b over 2a x plus b over 2 2a squared minus b squared over 4a squared plus c over a is equal to 0. Right? So if the 2's there cancel out, just leaving b over a times x, and you get a b squared there, and a 2a squared would give you a 4a squared over there. Now, from yesterday when we did factorizations, you know that this is equal to x plus b over 2a squared. And we'll move that stuff over to the other side. It's b squared over 4a squared minus c over a. We can put this all in one fraction. So that becomes b squared minus 4ac over 4a squared. Right? Yeah. Okay. Next step. We have x plus something squared is some constant. So we just want x on the left-hand side. So we take the square root of this to get that x plus b over 2a is square root of b squared minus 4ac over 4a squared. And since you want some value squared to be this, you need to keep in mind that it can be positive or negative. So you put a plus minus in the front. So if you square this side and you square that side, no matter what sign you have over here, you'll still get back to the previous statement. Okay? Next, we just have to move that b over 2a over. So get that x is minus b over 2a plus or minus the square root of b squared minus 4ac over 4a squared. Now you have a square in the denominator, which means you can take it out of the radical to get minus b over c plus minus the square root of b squared minus 4ac 2a. And put those two together, get minus b plus minus the square root b squared minus 4ac over 2a. So that is a general solution for the roots of a quadratic polynomial. It is worth remembering this formula. You'll do it in grade 10, grade 11, but just, yeah, if you know it now, it will save you a lot of trouble later on. Yes? This one. So, if you want an example of it working, take, I don't know, x squared plus 5x plus 6 is equal to 0. So, according to the formula, the solutions to this would be x is equal to negative b, so minus 5, plus minus the square root of b squared, which is 25 minus 4 times 6 times 1 over 2. So that means that x is minus 5 plus or minus 25 minus 24 is 1. So plus minus 1 over 2, which is minus 3 and minus 2. Cool. Okay, so you know that minus 3 and minus 2 are roots, and you can plug them into that to check that it works. And this is actually a useful way of factorizing quadratics that you can use at school if you want to, but don't tell your teacher. So the fundamental theorem of algebra said that we can get something with at most 2 degree, but it turns out you can always get linear factors, but then you have to start working with complex numbers. But in this case, you have 2 real solutions, so you will get 2 linear factors with real coefficients. So if you let x squared minus 5x or plus 5x plus 6 be some, so the leading coefficient is 1, so it would be a 1 over there. So you have x plus r1 times x plus r2 over there. According to the fundamental theorem of algebra, we are allowed to do that. From here, if this is 0, then at least one of those two needs to be 0. So when x is minus 3, one of those two needs to be 0. Suppose that it's x plus r1. If that's 0 when x is minus 3, then that means r1 is equal to 3. And if you do the same thing with minus 2, you get r2 is equal to 2, from where you get that x squared plus 5x plus 6 is x plus 2 times x plus 3. So you can do this for any quadratic. You just find the roots and then put them into the linear factors there. Okay, just one thing. So you have this square root of b squared minus 4ac term over here. So for this to make sense in real numbers, you need this value to be positive. But there's nothing stopping it from being negative. You could have, for instance, like b equals 1, a equals 1, and c is like 10 to the 10, or something ridiculous like that. So it turns out this thing, and this b squared minus 4ac is written as a delta. And this is known as the discriminant. So if delta is less than 0, then you have no real solutions. And if delta is greater than 0, you have real solutions. And if delta is equal to 0, you have a single unique real solution. For example, if you consider something like x squared plus 2x plus 1 is equal to 0, according to the formula, then x is minus 2 plus minus the square root of 4 minus 4 over 2, which just gives you minus 1 plus or minus zeros. So there's only one solution to this. And what that means is that you do still have two solutions, but they're the same thing. So in this case, x squared plus 2x plus 1 would be x plus 1 times x plus 1. Two roots, but they're the same thing. Oh. Okay. So we've done linear and quadratic. And that's really useful for polynomials because those can always be linear or quadratic factors. But you may be wondering if it's possible to do the same thing that we did there for higher powers. So is there a general way of finding the roots of a cubic or a quartic or a quintic or something like that? So it turns out that cubic equations do have solutions similar to that, where you have a formula that describes all of the roots. But I think it takes like half of this board to write it out, so we're not going to do that. There's also one for quartics, which takes up both boards, so we're not doing that. And for any degree higher than that, there are no general solutions to that. Okay, but that doesn't mean that we can't find solutions in general. That doesn't mean that all polynomials of degree greater than 4 cannot be factorized nicely. For instance, with an x to the 5 minus 1, you can still factorize that as linears and quadratics. Yeah. Okay. So, next up, we spoke briefly about complex numbers. Don't worry too much about what those are. So, sometimes with polynomials, you want to find solutions that are only from a specific set. Like yesterday we spoke about real numbers, natural numbers, integers, rationals, all of that jazz. So there are a number of ways of determining how many solutions a polynomial could have in a certain set, or show that it doesn't have solutions in a certain set. So, for instance, if you have, let's say, if you have something like a combinatorics question where you have to find the size of some set satisfying whatever it is, and you get that s squared plus 5s plus 6 has to be 0. That means that s is -2 or s is -3, which doesn't make sense for the size of something because the size can't be negative. So it would be nice if, when you're dealing with stuff like this, you could stop a few steps shorter and save yourself a lot of work. Okay. So, in general, the number of complex solutions is equal to the degree of p. And p is a polynomial of degree n, so this just be n. Okay, but this isn't necessary most of the time. So the number of real solutions is less than or equal to n. And specifically, it's n minus sum 2 times k, where k is some natural number, or counting number rather. Okay? That's some counting number, 0, 1, 2, 3. Okay, and the reason for that, if you're interested, is that complex solutions always come in pairs. So if you just want real solutions, get rid of the complex solutions, which would be taking out 2 at a time, which means it's less than that by some even number. Okay, if you're interested in learning more about how roots behave, you can look up Pietti's formula, which we won't do now. It's a senior topic. Okay. Next up, a nice property is if the degree of p is odd, then p has at least one real solution. Okay? Does anyone want to try and prove that? Yeah?
So the argument that I would make is, if you look at any polynomial with an odd power, and you look at the Cartesian plane, the function is either going to have a negative or a positive leading coefficient. If the leading coefficient is positive, it is going to be positive in the first quadrant. Otherwise, it's going to be negative in the first quadrant. And similarly, if the leading coefficient is negative, it's going to be positive in the second quadrant. And then, so basically, the argument that you make is that polynomial has to cross the x-axis at some point to reverse from quadrant 2, positive in quadrant 2, to negative in quadrant 4, or from positive in quadrant 1 to negative in quadrant 3.
Okay. Yep. So that's one type of proof. So the idea is that you can write p of x as an x to the n plus some polynomial O of x, which is something x to the n minus 1. You don't really care about the other coefficients, just the leading one. So we'll assume, without loss of generality, that an is bigger than 0. which just means that if we did a(n) less than 0 to be the same argument, but some signs would change. With the idea being that there exists some k greater than 0 such that a(n) k to the n is bigger than OK. Well, minus. Yeah, so yes, I'll do that. So that means that at some point for some k over there, for all x greater than k, p of x is greater than 0. Similarly, there exists an owl less than 0 such that, or even it doesn't have to be that, it could just be element of the reals, such that a(n) owl to the n is less than minus o owl, which is to say that for there exists some k such that for all x there, and there exists some owl such that for all x less than owl, p of owl is less than 0. And since p is a polynomial, which is a type of function known as a continuous function, if you look at the graph of it, there's some positive value where the point of p would be up there, and there's some negative value where it's down there. And these 2 points have to be connected somehow when, this is when n is odd. But, yeah, you can check that just by making k very, very small. So the idea being that if you want to go from that point to that point with some curve where you don't have to pick up your pen at any point, then no matter what you do over here, at some point you have to cross that line. And this is only true for odd functions functions with odd degree. It doesn't work for even functions. For example, x squared plus 1. You can show that that's always positive. Okay. There is another way of doing this, which is slightly less, or it's more algebraic and less intuitive. Like so, we'll use the fundamental theorem of algebra to prove it. So, suppose that n is equal to 2a plus 1. Let's not use a, let's use pick a letter. N. Okay. So let n be 2s plus 1, where s is an element of the counter numbers. Then we know that p of x can be written as an times r1 x times r2 x, and so on until you get to rk x. Let's change this to be a t, I guess. Now you look at the degrees of those factors. So when you multiply polynomials, the degrees add up. So if you have x cubed times x, you get x to the 4. So the degree of the left-hand side of the degree of the product is the sum of the degrees of those factors. So you can say that n is equal to the degree of r1 plus the degree of r2 plus plus the degree of rt. And by the fundamental theorem of algebra, all of these terms are less than or equal to 2. So n is 2s plus 1, and that's equal to some sum of things over there. Now, suppose that there isn't a, okay, if there is a real root, then you can write, suppose that p of r is equal to 0, where r is some real number, then you know that x minus r is a factor of p. And this is known as the factor theorem, but it's just a direct result of the fundamental theorem of algebra. So if there is a real solution or a real root of this polynomial with odd degree, it can be written as a factor with degree 1. So let's suppose that there isn't such a factor, which means this must have degree 2, this must have degree 2, so on and so on, that must have degree 2. You have a sum of a whole bunch of 2's, which has to give you an odd number. So that can't ever happen. So there has to be at least one factor of degree 1, which means that there must be a real solution to p of x equals 0. You happy with that? Okay. So that is for real roots. Now we'll look a bit more specifically at just positive and negative real roots. So So Descartes' rule of signs is a way of finding the number of positive real roots and the number of negative real roots. So consider the polynomial p x is a n x to the n plus a n minus 1 x to the n minus 1 plus whatever plus a1 x to the 1 plus a0. The rule says that the number of positive roots is less than or equal to the number of times the signs of the coefficients of p of x change. And similarly, the number of negative roots is less than or equal to the number of times whatever that p of minus x change. So it's the same thing, just change that plus x to minus x. So we can see this in an example. I know the definition doesn't make much sense, but it's a really cool thing to know.
Isn't it specifically, you say less than or equal to, but isn't it specifically an even number less? So like if you get 4 sign changes, it's 4, 2 or 0.
That makes sense. I'm not sure of the details, but yeah, that sounds right. Okay. So consider x cubed minus 3x plus 2 is equal to 0. Now you could try and just find all of the roots and count how many there are, but sometimes that's really hard to do, so factorizing that is not fun. So you use the rule of signs. So the coefficients are 1, minus 3, and 2. You ignore the 0 coefficient. So over here, the sign changes. It goes from a positive value to a negative value. And over here, the sign changes as well. It goes again from a positive value to, oh, sorry, this should be a negative. So here, the sign doesn't change. So that tells you that there is at most one positive root. Okay? I would do the same thing for minus x. So you put in minus x wherever x was, minus 3, minus x, minus 2, 0. So that's minus x cubed plus 3x minus 2 is equal to 0. And the coefficients there are minus 1, 3, and minus 2. You look at the times that this changes sign. So this one there, this one there. So there's 2 of them. So that means there's at most 2 negative real solutions. And you can check this because it turns out that x cubed minus 3x minus 2 is equal to x plus 1 squared times x minus 2. Which means that the roots are x is equal to 2 and x is equal to minus 1. And since there's a square, you can count this one twice. And the rule of signs told us that we could expect at most one positive root. We found exactly one. And it said we'd find at most 2 negative roots. We found exactly 2, but they happen to be the same thing. Yes?
So you take the original number and then you just change the sign of each.
You change the signs of the odd powers. Yeah. So minus x to even power would stay just x. So suppose you're looking for positive real solutions for something that's useful in a question somewhere, and you get that it has to satisfy x to the 4 plus 7,000 x cubed plus 10 to the 10 to the 10 to the 10 x squared plus Graham's number x plus 3 of G64 is equal to 0, something ridiculous like that. You can just notice that the sign never changes, which means that there is never a positive real solution. So there's no point looking for a positive real solution in that case. So that's how it's useful. You can see how those two things are related, because you could just consider. Okay, so the positive roots of p of x are the same thing as the negative roots of this p of minus x, this q of x. So that's why the two statements look so similar. Okay. Next up. So that was for positive real numbers and negative real numbers. So the next step would be to move to rational numbers. Okay. Rational roots are a lot easier to find because there's something called the rational root theorem. And this says that if p of x is an x to the n plus, you get the idea, a0, where I is an element of integers for all I, for all 0 less than or equal to I less than or equal to n, And if P of S over T is equal to 0, where the GCD of S and T is equal to 1 and S T does not equal 0, then that means that S divides A0 and T divides AN. So to put this differently, if you have some polynomial that has purely integer coefficients, yes?
I know it's a really bad time to ask, but what is the, like exponents at the top, what's the number at the bottom?
Where? This is the
Like the
subscript.
AN, yeah.
So that's just the index of that element.
What's it in?
Okay, so a lot of the times when you have a lot of variables, you like let one be A, let the other one be B, let the other one be C, and D, and so on and so on. And if you have 26 of them, you get to Z. And then when you have the 27th one, then what do you do next? You have to stop. Okay, so then you go to alpha, beta, gamma, delta, epsilon, etc. until you get to zeta. And then what happens when you need a 60th or 61st one?
Capital
Yeah, you can have A, B, and so on and so on. But that becomes really annoying to work with because you've used up all your variables just describing a list of numbers. So what you can say instead is that, well, all of these numbers are similar, so we can call the first one A1, call the second one A2, third one A3, so on and so on. And then you never run out of variables because there's always more numbers that you could use. So if you end up to A2019, there's no problem with writing that, unless you want to write out 2019 letters of all the alphabets you can think of. Yeah, so yeah, that's why that's useful. Okay, and also you can do what we did there, letting it go up to AN, which is to say that it doesn't, the size of the list doesn't depend on a value, or it's not a fixed size. You can choose whatever size you want for it. Okay?
And then how do you have A0?
That's just to make it look nice. So that n matches with that n over there. And then next up you would have a n minus 1 x to the n minus 1. Where the n minus 1 matches up with the n minus 1. And then you'd have a 1 x to the 1 over there. And then if you continue the pattern, you'd have a0 x to the 0. But that x to the 0 is just 1. So that's useful because you can also write your polynomials like so, if you want to. Which is a lot less effort than writing it out like that every time. And yes, you are allowed to use that. Don't be scared, as long as you know what you're doing. Okay? So back to this. If P is a polynomial that has purely integer coefficients, and you have some real roots, or some rational roots, where a rational number is written as a fraction between two integers with the one in the denominator not being 0, and they don't share any factors, all of that, then you know that S, the numerator, must be a factor of that last coefficient. And you know that T, the denominator, must be a factor of the leading coefficient. Okay? So, let's see an example. Consider 2x cubed plus 3x. Consider this equation over here. So that looks like a complete mess and doesn't look fun at all to solve. Because when you're trying to match up factors, you have to worry about getting those to match, things in the middle to match, and yeah, it's not fun. So you notice that those all have integer coefficients. Oh, and you're only looking for rational solutions. Yeah. At which point that theorem should pop into mind immediately. So if you ever see solve something for all rational numbers, it's going to use that somewhere. Okay, so what that says is that, okay, let's call this, pick a letter, Q. So if Q of X is that, and you want Q of S over T equal to 0, where S and T are two integers that don't share any factors, and T does not equal 0, then the rational root theorem says that S divides 3 and T divides 2. Okay? Next up, we can go further with this, because we know that S is an integer and T is also an integer. It has to be a factor of those two things, but there are only so many factors of those two things. So there's finitely many values that S and T could be. Specifically, 3 is equal to 1 times 3, but it's also equal to minus 1 times minus 3. Just keep that in mind, that factors of numbers have negative factors as well. They're the same as positive ones, just with negative signs. And 2 is 1 times 2, which is minus 1 times minus 2 as well. Okay? So what this tells you is that S has to be an element of the set minus 3, minus 1, 1, 3. And T is an element of the set minus 2, minus 1, 1, 2. Okay? So at this point, you can just make every single rational number that you can and check that it's a root. So you would check minus 3 over 1, minus 3 over 2, minus 1 over 1, minus 1 over 2, 1 over 1, 1 over 2, 3 over 1, 3 over 2. So you can keep in mind that minus 3 over minus 1 is the same thing as 3 over 1. So you save yourself a lot of work by just looking at positive denominators. So this is nice because this theorem tells us that if there is a rational root to that polynomial, one over there, it has to be in that list somewhere there. So, for instance, if you check P or Q of minus 3, you get 2 times minus 27, so that's minus 54 plus 3 times 9, so you get 27 plus 24 plus 3, which gives you 0, which means minus 3 is a root. Then you check minus 1. If you check minus 1, you get minus 2 plus 3, which is 1, plus 8, which is 9, plus 3, which is 12. So that's not a rational root. And you keep going through the list and you get that Q of 1 over 2 is 0 and Q of 1 is 0. So you found 3 rational roots there, and those must be all of the rational roots. Specifically, you found 3 rational roots, and you know they could be at most 3 roots, so you found all of the roots. So that makes you happy. Okay. We can go over the proof of this if you'd like. And anyone votes yes, votes no.
No.
I abstain. Yep, that's a yes.
Huh?
Okay, well, I don't think it's too bad, so we'll do that. I'm hearing a lot of yeses, so that's good. So you do the normal thing, let P be the polynomial with integer coefficients, whatever, and let P of S over T equals 0. Now you can use the way that polynomials are defined to get that an S over T to the n plus an minus 1 S over T to the n minus 1 plus whatever plus a1 S over T to the 1 plus a0 is equal to 0. The next step is to get rid of those denominators over there to make everything integers. So you multiply through by t to the n, and you get that an s to the n plus an minus 1 s to the n minus 1 times t to the n minus 1, t to the 1, plus s to the n minus 2 t squared. What? Should be a minus 2 there, plus a1 s to the 1 t to the n minus 1 plus a0 t to the n is equal to 0. Okay, and at this point you move the leading term over to get that minus an s to the n is an minus 1 s to the n minus 1 times t plus whatever plus a0 t to the n. At which point you notice that you can factorize that a bit to get an minus 1 s to the n minus 1 times t to the 0 plus an minus 2 s to the n minus 2 t to the 1, etc. plus a 0 t to the n minus 1 all times by t. Okay? So an is an integer because the polynomial has integer coefficients. Yes?
What do the s and the t stand for?
Those are two integers which are relatively prime, so they don't share any factors. And they're just representing some rational root. So over here we have an integer times another integer equals an integer times an integer. So this means they must share factors. In particular, t must divide minus an s to the n. Okay, but by definition, s and t do not share any factors. They're constructed to be like that, which means that t must divide an. And now you can do the same thing as we did here, but instead you move this last term to the other side and factorize, and you get that s must divide a0. Yeah, seems right. Okay, and that proves the theorem that we have up there. So you can extend the rational root theorem to be specifically for integers just by checking only when t is equal to 1. So any integer divided by 1 gives you an integer. So if you're only looking for integer roots, just check for factors of a0 and check if they're roots. Yep, so I think that's all for today. Did anyone get anywhere with those?
Can you do the first one?
Okay.
The answer is 246.
Sorry.
For number 1.
246.
Okay, I don't know what the answer is. Okay. And since P of n is defined, or Q of n is P of n minus n, you know that P of n is equal to Q of n plus n, which is 2n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 plus n. So that is the value of P. And from here, we can find that P of 6 is 2 times 6 minus 1 times 6 minus 2 times 6 minus 3 times 6 minus 4 times 6 minus 5 plus 6, which is 2 times 5 times 4 times 3 times 2 times 1 plus 6, which is 240 plus 6, which is 2, 4, 6, which is a lot bigger than 6. Oh. Any other questions? Okay. Then I think it's lunch, unless Liam wants to say something.
Solutions for today's test.